basic computer science problems that we're trying to solve. And the HPC community, especially academia and science community, have already solved most of these problems. I mean, these are basic computer science problems. At PayPal, however, the problem is that we have large-scale, real-time ingestion of data. We needed to figure out how to work with technology that allows us to deal with those. So we went to the HPC community. Well, basically we went to supercomputing about six years ago, and we went shopping, as my colleague says. We went shopping for gear that would help us solve some of these problems. So we also saw an eventual merge of industry and enterprise industry and HPC communities. Is anybody here from industry at all? No one. Oh, there's one. Great. 2, 3, 4. Great. So we kind of felt we were alone in that path. You know, there's the HPC world and then there's the enterprise world. So we're trying to actually start merging the two communities together. And we've done a couple of BOFs at supercomputing around how enterprise computing and how HPC architectures can merge together. So those were quite successful. We also saw HPC price points come down. You know, we're not going to buy a $100 million supercomputer for using for our use at PayPal. It doesn't make sense economically. So we did find a lot of hardware and technology at price points that we thought were feasible. So that's another reason that we started leveraging HPC. All right, so here's a quick timeline. You've seen a lot of these in the last day. And it's driven by innovation. So the innovation has to keep moving forward, otherwise the company becomes stagnant. Innovation in terms of new algorithms or new ways of using devices or new fraud detection methods, anything that will give us a competitive edge, we have to innovate on. Otherwise, you basically just stay stagnant. So in 2008, a little bit after 2008, we had started building what we call Trinity. And Trinity was essentially a giant graph database that we link people and transactions and IP addresses, et cetera, together. And it is very successful to understand how people are interacting. And so we started leveraging it as a real-time fraud detection system. And around the same time, we said, okay, we're going to start using HPC to do some of this work. So that started in 2008. In 2012, we started doing HPC big data analytics. All right? So there's a little gap there, but it's not because we didn't have funding. It's just that we were so busy trying to implement what we already had to move it to the next level. In 2013, we started looking at something that we term systems intelligence, and that's taking interactions of systems and understanding how they actually behave together so that we can model out future capacity needs or correlations between events and how we can adapt those to meet needs on the business and operations side. And I've got a question mark for 2015 only because we know we're going to keep moving forward. We've got some great ideas that we picked up from Supercomputing 2014. Some new technology we saw there that we're going to start looking at. But the other thing is that we are splitting from eBay, and that's kind of the next 4 or 5 months is going to basically be focused on that. And unfortunately, we can't continue the trend that we've been doing right away. But we're really excited to go to ISC and look at stuff there. So that'll hopefully all pan out in the end. All right, so real-time fraud detection. I use the term fraud detection only because it's a buzzword. But what I really want to showcase here is that we are trying to look at fraud and risk and things like this in a completely new way. What I'm going to be talking about here is only one particular fraud detection system that we have. Okay, we have very many, and I don't know what they all do, and I can't, because I don't know what they do, I can't really tell you what they do. But this is one particular fraud and risk detection system that we put together. It's very, very difficult to do this in real time. How many people get a call from their credit card company saying, "Oh, look, you know, you've got a new charge," and you say, "Well, you know, why didn't you stop it from actually happening before it happened?" It's very, very difficult to do, and we're trying to do that. So we go back to the patterns that I mentioned earlier. We look for patterns, suspicious patterns, in real time. That's also very difficult to do because you don't know what the patterns are. There's always new patterns. The bad guys are smarter than us. They're looking for other ways to do bad things. All right. We wanted the ability to create new models for looking at fraud quickly and efficiently and move them back into the production stream. So if we notice some aberrant behavior going on in the offline world, we want to take that model or preventive model and push it into the real-time world as fast as possible. And we wanted to provide an environment for people, especially data scientists, to look at different ways of modeling the data through analytics, through visualization, using MapReduce, using dimensioning analytics databases, etc. So between all these different problems that we had, we came up with a whole bunch of other challenges, okay? So we are up 24/7, 365. We're available all the time, which is a complete different method of looking at it than most of you are used to. You know, you have large systems, but they don't need to be available all the time. We do, all right? And how do we keep the fraud models current and ensuring that bad guys cannot do bad things? So we created this giant graph. Unfortunately, you know, our talks and our discussions with the HPC community has led us to Oak Ridge. We're doing some work with Oak Ridge around graph modeling. We're doing some work with IBM around the graphs, only because we cannot the computer science problem is very, very large, and it has to be a PhD or a faculty that can help us with that, as well as the technology required to do these large graph patterns, subgraph pattern detection. All right. We also wanted to keep the operations team very small and very simple. The reason for that is we don't want to make a large operations team because HPC, the knowledge required to run HPC systems just is not there in an enterprise world. All right. And the other thing is we wanted to educate our peers and our upper management and make them understand what HPC really was. Because if you say HPC to somebody in the enterprise world, they go, what is that? Is that a new, you know, whatever? So it's basically education and teaching our peers what HPC was all about. All right, so what kind of volume are we talking about on this particular HPC fraud detection system? We're doing about 11 million logins a day, all right? We do about 14 million financial transactions a day. Each of those transactions can calculate about 500 different variables. So if I did a transaction with Brian, for instance, there's just two people transacting, but that particular transaction can generate up to 500 different variables. We do about 4 billion inserts into an OLTP database and about 8 billion selects a day into an OLTP database. All right, so, you know, not extreme numbers, but difficult to do in real time as it's happening. So we built a system called Trinity. And it's basically, as I mentioned, a real-time linking platform for different identities, transactions, IP addresses, credit cards, bank accounts, etc. And as you can tell, all this data, once you start putting it together, generates a graph that just exponentially grows over time. We wanted to use highly distributed open source databases, so we used MySQL in this case. It is 7 years old, so we're looking at other possibilities. Some of the new NoSQL databases that have come out. We're very pro messaging. Messaging is what we really like to do. So we do a lot of messaging, message routing, data marshaling, etc. We do a lot of in-stream analytics using complex event processors and event stream processors. So for instance, if you don't know what those are, if you are counting fish in a stream that's going by, you're not going to go do it manually like this. You're going to put a fish counter in the middle and have the thing trigger every time a fish goes by. So we do use complex event processors a lot. We use open source one called Esper, which works for us. We can scale it horizontally. We obviously do downstream analytics, Hadoop, HDFS, all the regular offline analytics platforms that are available. And of course, we leverage HPC architecture where it makes sense. There's no point in spending a lot of money and putting HPC on the front end as a web server. It doesn't make sense. So we put it in place where it does make sense. And of course, standardizing operations, command and control, partly because of the enterprise world that we come from. All right. So here's basically the flow of the system. Some of you might have seen this before in other talks. But we essentially start at the very top. Got a one. So proprietary message come in to the top, and then there's also a REST interface and a SOAP interface. The blue area is the enterprise side of things, all right? And the yellow is HPC. The transaction comes in from the top. It goes into what we call a service gateway pool, which is basically a message router. So the transaction that I did with Brian comes in at the top. It figures out Brian. It figures out me. It puts that transaction into what we call the TIS database here. That's actually not one database. It's 1,800 databases. I just did it simply because I don't have space for 1,800. But this all happens. This is all MySQL, and there's just pools of servers here. So this could be, I think it's 128 servers. There's 64 of these. Everything's scalable, horizontal, distributed. We then drop into something called, that transaction gets dropped into something called Cerulean. You'll notice the Cerulean Azure Cobalt. There's a blue theme going on. I'm not sure why that is, but Cerulean is basically a message routing system, and it sends messages to different areas. This is the main message bus, but the messages go to different areas. I'm number 3 now. And it goes to Cobalt, which is a store and forward system. Basically, we can capture the messages and replay them later on. If we do notice some strange behavior, we can replay them into a different system. Azure here is another set of databases, which is basically the metrics database. So every transaction gets the variables I mentioned, 500 up to 500 metrics. So if Brian and I have done a transaction, it figures out Arno and Brian have done a transaction 3 times in the last year. So it increments a bunch of counters, for instance. Or Brian's coming from a different IP address, that gives them a -1. So there's these metrics going on that we capture on each transaction. And then, oops, getting ahead of myself. Indigo here is actually the scoring engine. So that particular transaction that Brian and I are doing gets scored based upon models that exist in these complex event processors on these different applications. All right. So let's just recap. Transaction comes in, everybody gets identified, gets added to the graph in a relational database, goes through a message system, goes to the store forward, goes into the metrics databases to get each variable added, goes into the Indigo scoring engine to get scored, and then the message goes back out to PayPal proper and says, okay, this transaction is fine, it gets a score of 1, all right? This complete flow from top to end takes about 150 milliseconds. And that happens thousands and thousands of times a second. All right, so we ended up buying SGI Altix ice boxes. This is a picture. This is from 2008. This is a picture of the installation. The boxes are here. These are all SGI disk drives here running the databases. I can see the SGI people smiling. But you can tell, I was a little bit, we only run 156 sockets here. And it's not 100,000 like most of you are running or 10,000 or whatever. So we have a very small cluster, but it's, for our purposes, very, very efficient. So this is basically, in essence, everything you saw in yellow on that previous slide, that's what this is all running here. All right. This is a diagram of what an actual cluster looks like. So each of those databases and each of those application nodes I showed you on the previous slides. They fit inside this cluster. So basically each node has a different purpose. But we can alter each node to have a different purpose very, very easily. Everything virtualized. So for instance, we have all the databases in purple. We have the messaging, the cobalt thing that I showed you earlier in light blue. But I just wanted to show you the variety of processing and the functions of each of those different boxes and how they're working in the cluster. This is statistics from Cyber Monday just last year. For our particular system, not all of PayPal, but for our particular system, we had some fairly impressive numbers. This one's obviously because I'm a database guy. This is sustained 235,000 database operations a second. All right, so it's not like flat all day long. It goes up and down, up and down. So this could potentially go to 900,000, 3 times X in a second database operations. The numbers are very significant because we have to stay up all the time. So these numbers have to be available to the business all the time. Big data analytics is the next part. And I know DK is going to talk a little bit about it later on after the next talk. But I want to talk a little bit about what we are doing with big data analytics on the HPC side. So in 2010, we started looking at Hadoop, and we came up with an idea that potentially Hadoop, as you buy it from a vendor, might not be exactly the best configuration for it. So we looked at all 3 components, memory, CPU, and disk. And we said we have to start separating those 3 things out because they scale differently, right? If you buy commodity boxes for Hadoop, you're always going to have the same scale factor. We decided that we wanted to separate all the 3 different parts out because you're going to use more storage than you would CPU, or you're going to use more memory than you would CPU. So we started separating things out, and we also decided that for sort and shuffle, we should use faster disks. So we put SSDs in there for sort and shuffle. We brought Lustre in to do all the ingress work. So drop the file once and leave it there. You don't have to move the data around, right? Which Lustre is perfect for doing. We bought a company called Where.com that does geo-location marketing. And they're using the Hadoop cluster for analytics on geospatial shopping. And the funny thing is they had been using their program on our traditional Hadoop systems, and they kept coming to us and saying, hey, this thing is running for 7 days and it breaks. Is there some way you can help us look at it? So we looked at their workload and we said, oh, just put it on our HPC cluster. It's going to work fine. So their 7 days plus a breakage turned into a 2-hour job for us. So it's the right workload for the right technical environment. Not every job's going to run in 2 hours. Not every job's fits into an HPC cluster. But what I want to, showcase is that it is possible to take existing jobs that take too long and move them to an HPC cluster and actually have them run faster. We also store a lot of different technologies on that cluster, on the Babar cluster, analytics database, R, MATLAB, etc. These are all things that you guys are used to. So the Babar cluster was another SGI box, another 8400, and it kind of looks like this. There's 2 of them. And we use InfiniBand, obviously, as the interconnect, DDN storage for the Lustre piece storage. And the typical, not a lot of cores, but enough to get the job done for us. All right. So the problem with big data analytics is everyone seems to think that Hadoop is the answer. And as we heard from Addison yesterday, it's not, right? It's just not the answer to everything. We look at it as a 3-legged stool. We need to have, for our purposes, we need to have the OLTP side to get the data in and to drive it. We need to have analytics database, i.e. Vertica or HANA or some of the others, so people can run SQL queries, right? HDFS is still available for Hadoop. We also need to have graph analytics available. So between all three of these things, you might have a complete environment for running analytics. And this is something that enterprise doesn't quite understand. They're not sure about graph. They're not sure about a real analytics database. All they know about is Hadoop. So we said, look, if you want to do big data analytics, you need to have all the pieces in place. And this is kind of a struggle that we're having with a couple of the groups that we work with, because they're not looking at the holistic picture. And I'm sure that a lot of people here understand the difference between the different that we're talking about. All right. So the third part of our HPC evolution is called systems intelligence. And this is the latest one that we've been working on for the last year and a half. And what I mean by systems intelligence is we want to maintain the wellness of the PayPal ecosystem. And that seems like a big phrase, but if you really think about what it means, is what we are trying to do is look for anomalies in real time of all the interactions between all the systems and all the applications, so that we can detect patterns before they actually impact our systems and operations. All right, so we call it operational analytics, which is a term that's been bandied around for a little while, but we're actually leveraging HPC to be able to do this. All right, so this is the slide that I'm going to present for socially responsible computing. This is a data center in Salt Lake City. This is an eBay data center that we are hosted in. It's a beautiful picture. It's one of the greenest data centers on the planet. It runs on Bloom fuel cells, so there's no coal, there's no carbon footprint. But what I want to describe is all the stuff inside that data center, right? No matter how much you save in power and clean power, you're still consuming the power that all those applications and servers are running inside there. So operational analytics, the systems intelligence piece that we're working on, is trying to figure out, well, how do the servers behave during the day? So traditionally, in the US, when PayPal was first started, it would be, peaks and valleys during the day. The peaks would come at noon, they'd come after dinner, people are paying each other. Sundays are a big day for us. And we want to understand how we can start turning off VMs, for instance, during the day so that we can start saving power. And that's a large challenge. How do you make sure that the VMs are spun up again for the next cycle moving up where people are going to start paying? So that particular problem will save the company millions and millions of dollars. If you can turn off or at least have your system be smart enough to understand when it should turn itself off during the day or at night, how do you solve that problem? My colleague and I have an even greater vision. And this is going to sound crazy, but they told the Wright brothers they were crazy too. We want to be able to take the whole data center and move it around the planet. All right. By that I mean, can we move all the applications around the planet while during the night where energy is the cheapest? All right. So it's a vision we have, and we might get there someday, but we have to start small. So we're going to do it this way. All right, so the problem that kicked off this systems intelligence project with HPC was there's no analytics being done on the machines. All right, nobody's taking machine data, nobody's taking data center metrics and actually doing any of the analytics around them. There's no understanding how this could even be analyzed by operations teams. Operations teams are operators. They're not data scientists, they're not data analysts, they're not architects, right? So they've been gathering all this data, all these metric data from machines, and just tossing it. There's no interest for the business side because the business people are only interested in business analytics. They want to know how many people came last quarter. They want to know what the revenue model is for last year. They're interested in business metrics. They're not interested in operational metrics. All right. There's no future benefit of integrating to other operational data, right? But the vision is there. We have a vision, and we're going to showcase that. And so we stepped in and we said, look, nobody's looking at this data. We want to take the data and start modeling it and start to understand how we can actually leverage it to be good corporate citizens in a green world. We want to understand that data so that we can actually look for patterns that can create problems and minimize downtime and increase customer satisfaction. And because we'd already proven an architecture that was feasible for this with the fraud detection side, the Trinity side, they said, okay, go ahead and do what you need to do and get back to us when it's finished. So we said, okay, we're going to take an ecosystem, and this is Mother Nature's ecosystem. Basically, it's perfect, right? Temperature is perfect, water flow is perfect, the fish are perfect, the coral are perfect. It's very symbiotic. Everything is a perfect system, okay? But what happens when an oil slick comes through here? Not a good thing, right? That ecosystem starts to degrade rapidly. But what we were trying to understand was, how do we take our data center and the applications in it and the servers in it, the network in it, the air temperature, the airflow, how do we take all that information and gather it together so that we can actually model this in HPC? So we're trying to take this very static, well, dynamic and static model and try to do this in computers. So what were we trying to accomplish? Well, a few things. We wanted to gather a holistic view of what that environment looked like. All right. We wanted to create a self-healing environment. Right. So when we find a problem with a server, we're going to take that server out of commission and spin up a new VM to take care of that. We want it to be self-healing. We don't want any human interaction because humans cannot react fast enough, and our systems have become so complicated and so complex that not a single human can understand them anymore. We're teaching the machines to learn about themselves. We wanted to understand the capacity of the system. It's great to say, okay, we're going to order 1,000 web servers and let them run. But if nobody understands the capacity of what those web servers can do, you're overspending or underspending, which way you want to go. But no one's taken the time to understand what the machines are capable of doing. We wanted to leverage real-time streaming analytics that we leveraged in the fraud side to look for patterns and anomalies as they're happening in real time. And again, we wanted to educate our peers and management about the use of real-time analytics augmented by HPC. So what are we up against in this particular situation? All right, so we're looking for real-time anomalies based upon historical data and patterns that we found. The streams that we have available to us are application logs, server metrics, data center metrics, and social media. So we're doing 3 million events a second. We're not doing it today, but we are going to be looking at about 3 million events a second for anomalies. All right. 25 terabytes of data ingested every hour. 20 megabytes of machine data a second. This is a relationship graph of 50,000 metadata relationships between the applications. Some people think this is a molecule from the late 60s, but it's not. And there's an increase in social media trends and customer service interactions. So if we take all those 4 things, and we can start adding more, we generate a huge amount of data and a huge number of interactions between that data. All right, so again, our system is called Systems Intelligence. We needed to create a common ontology between all those events. And I've got slides on that, but they're really, really boring, so I left them out for this talk. We wanted to build purpose-built systems to do this work. We're going to use RDMA to do memory sharing between servers. Cluster file systems, like I mentioned, to reduce copy times of data. So we drop the data once, act upon it. And we again use inline streams for doing the complex event processing, and downstream analytics for model building and further processing. So this is the flow for systems intelligence. We have our 4 sources at the top: application logs, machine data, environmental data, and social data. We're very, very lucky that the application logs are coming from an existing system called CAL, which is called Central Application Logging. And it just generates every application, every call in the application generates a little log and says, okay, I'm in this procedure, I'm in this function. So it's generating terabytes and terabytes of data an hour. But it goes off and it gets stored and it never gets looked at. So we said, well, we'll just grab those messages and start consuming them for the particular pieces we're interested in and start analyzing those to understand the different events that are happening. All right, so they get thrown on a message bus. Again, messaging is very important to us for a number of reasons. It's scalable, right? If you need to have more applications receiving data, just have it subscribe to the bus. We have inline processing happening. Again, you'll notice similar to our other architecture, but that's only because we have to merge the enterprise piece, which is in blue again, with the HPC piece, which is in yellow. So there's very common architectures between what we built before and what's happening today here. Large window here. Again, what we're trying to do is store as many events in memory as possible so that when you're looking at that stream in a rolling window, you can look for different events that are correlated together. We have our offline databases here for adding extra data to those events as needed. We use Vertica as a back-end data store for just a set number of events so that we can analyze them. And we've got some visualization and machine learning, and our data scientists here are building new models and pushing them back up into the complex event processing stream. And any self-healing that comes out of this process gets sent to the self-healing remediation centers. So this particular flow is quite representative of the other flow I showed you, but this is also happening real time. This piece at the bottom is done offline, so we'll basically take a snapshot of the data for an hour or two, analyze it, look for new patterns, have our data scientists push things back into the complex event processors, and just keep doing this. So what we're trying to do is if PayPal releases a new piece of code on Thursday night at 11 o'clock at night, which it does, the first people that get affected by that code is somebody in Europe because of the time difference. So if somebody in Germany goes, well, wait a second, my application is not working the way it should, they're going to get on Twitter and say, oh, PayPal's just not happening today. Or they're going to make a phone call to our customer service center in Ireland and say, okay, there's a problem here. That process used to take a few hours to understand what was actually happening. With this particular system, we can detect it hopefully in less than 5 seconds, that there's a possibility that the Twitter feed is being impacted by something that the application is now doing. So we're able to start looking at this from the correlation engine between different disparate events from heterogeneous systems. And the only way we could have done this is using HPC. Enterprise could not have supported this at all. And we ended up buying a UV2000, which we installed in January last year. The UV2000 because we wanted a large shared memory box. We bought one with 6 terabytes. When we installed it, I think the ladder's just for moral support. But we have a bunch of, again, DDN arrays for storage. And this is basically what our cluster looks like. So we have our other cluster, which we had termed the bar, and it now gets added to our UV2000, the big brain, with a bunch of hardware, again, InfiniBand interconnects, and storage. So our clusters are getting slightly larger every time, and hopefully in a couple of years it'll be even larger. All right, so what can we do with the analytics that we have out of this? Well, we have a rolling window of events. I already explained that. The event window size is dependent upon a number of per second coming in and the size of the event. So hopefully within 6 terabytes, we can keep millions of events to look for different patterns that we've figured out and correlate them together. The shared memory also allows us to have different processes act upon it. So we've already heard about SHMEM. We're not using SHMEM yet, but it's very intriguing to us because we can have multiple clusters that are physically separate. But we can have many different particular boxes, be they big boxes, little boxes, all act upon that shared memory looking for different things, looking for different risks, looking for different models, looking for different patterns. The really cool thing is that we can do historical analysis and predictive modeling off of deep learning that we do. So we can take the models that we learn offline and push them into the stream and make the models even better than before. So what can we tell from doing all this? Well, one of the things we can tell is if an application flow starts to slow down, what is that from, right? If it takes you longer to log into PayPal, what is that from? Is it from a bad database select? Is it from a CPU that's having a problem? Is it from a VM that's having an issue? We can now detect this in real time and take care of it. We can maybe see something that there's a HVAC unit that went offline, right? Temperature has increased. Humans might not notice it right away, but our system might notice it because as an ecosystem, if the temperature in the water around those corals start increasing, they're not going to be happy. So we're basically taking the same analogy and saying, if the temperature in the data center starts increasing, potentially servers are going to start overheating and CPUs are going to act up. Bugs in code will show up a lot faster. All right, we've got people that are looking at our application and they can't log in for whatever reason. They're going to call customer service. It might be a code push that caused the bug. And of course, we have real-time business metrics. We can now actually input things like how many transactions a second are happening right into the stream, so we don't have to wait for reports at the end of the day. We can just tell immediately what's happening in real time. All right, so the business side of things, the visibility and the benefits, we have a healthy ecosystem. We have visibility into the whole thing. All right. Self-healing, obviously important. Minimize downtime. We want to model the whole PayPal infrastructure. Less relying on humans. Humans don't need sleep. Computers don't need sleep. And as I mentioned before, the systems become too complex for any group or any human to understand. The cost to the business, all right? Running a more efficient system is huge, right? If you can make the data center power costs decrease and increasing availability, you're going to save money at the bottom line, you're going to increase money at the top line. So having this systems intelligence in place is a huge benefit to the company from a business perspective. Now, what's happened out of what we were working on with real-time analytics is a project that we've embarked on, and we call it complex event complex event processing as digital signals. And this is something that we embarked on about 1.5 years ago. And Rich actually videotaped us at the HPC User Forum in September. The video is online. I'm only doing a part of it, but the video is online if you want to check it out. I think it's had 1 million hits now on YouTube because people are really interested in this thing. Anyways, what this is all about, I'm going to give you an analogy and talk about it a little bit. So I'm a big music guy. I like music a lot. I'm really looking forward to the presentation this afternoon on HPC music. But everybody likes to go to concerts, okay? I'm a big concert goer. I like to go to rock concerts. I'm actually going to see this band called Marillion in a few weeks. Classical, SFO, the opera, Wagner, and some organ recitals. So everyone likes to go to concerts. At least I do. Hopefully everybody does here. So the concert experience starts out like this. You go to the concert, you're listening to your favorite song by your favorite band, you're having a really good time. Might be some mood-altering enhancements, but you never know. You're really enjoying yourself with your friends. You had a glass of wine. And then all of a sudden you hear a bad note, right? But it's just a bad note. It's live. The musicians are doing whatever. You don't really care too much about it, so you just let it slip by. But what just happened when you heard that bad note, okay? Well, you analyze data in real time. Your brain picked up that bad note in real time. It didn't happen a second later or a minute later or a day later. It happened while the stream of data was coming to your ear, all right? At the instant that event occurred. So you used a predictive model, right? Your knowledge of the song, your knowledge of the lyric, to pick up that particular anomaly in real time. So that's basically what we're trying to look at when we're doing these real-time analytics. Oops. So we want to take that real time, not an echo of the event, but the actual event, understand how that can be modeled. Difficult? Yes. But how do we create a solution that allows us to do this faster, cheaper, and greener? That's the socially responsible computing coming out. We want to make things greener and cheaper. All right? So keep that in mind for a second. About a year and a half ago, Ryan, my colleague, and I were in a meeting with HP. And they were presenting their Moonshot server, which we'd already had a beta copy of, or a hardware of, for quite a while, and we were already testing with it. And we were in a meeting, a phone call meeting. There's nobody from HP here, but and they were describing these new cartridges that they have. So basically, for those that don't know, the HP Moonshot is basically a 3 or 4U box. It has 45 different cartridges inside it, and each cartridge has different configurations that you can put together. And it's very, very energy efficient. That's why we like it. So we were in this meeting with HP, and they were going through the different cartridges that they had. And so my colleague goes, okay. So they're browsing through cartridges, and he goes, wait a second, puts the phone on mute. He goes, hey, do you think this thing will do what we want to? So we said to HP, okay, can you go back to that one slide, and we want to that for a second. So we had an idea about this thing called Keystone 2 cartridge from Texas Instruments. And idea. It's one of these crazy ideas that people think that we have. And we said, let's talk about this for a second, because we have an idea about this particular cartridge that we can maybe use for a particular problem we have. And so we looked at the cartridge, and it has 4 arms on it. It has 8 DSPs. It's got fast interconnect and intraconnect. Got shared memory. And we looked at that, and we said, wait a second. That looks like HPC on a sock, which it is, if you think about it in that terms. All right? So they were wondering what we wanted to do with it. And we said, well, we want to do real-time analytics with this cartridge. We want to take text analytics, convert them to digital signals, and actually run them through the hardware to do pattern analysis. And so they said, okay, well, we don't think that can be done. We said, no, we can make it happen. So we want to do it faster, cheaper, and greener. All right? And so it's not impossible to do this. What we'd started to look at was complex event processing through the DSPs. And for those that know, so we've all been hearing about ARM, all right? Addison mentioned it yesterday. It was mentioned quite a lot at Supercomputing 14. But for us, Linux on ARM works because we're an enterprise shop. We know how to run Linux. We know how to do data marshaling. It gives us real-time parallel processing. All sorts of different things, global shared memory. And so what we started to do, looked at how we can leverage this particular cartridge to do what we needed to do. And so it gives us a bunch of different things that DSPs have been very good at for a number of years. 40 years of DSP program have already put all these great algorithms into the chip. So what we started to do was take text data that was being streamed in, convert them to floats, if you will, and then started matching patterns through the DSPs using about 150 lines of OpenCL to do the work. And the work is based on moving the data between the memory between the DSPs and the ARM cores. So we were quite excited about this, and we showcased it in September. And the bottom line is that we were able to achieve 11.2 gigaflop a watt of performance off the one cartridge, the DSP cartridge. And so across 4 socks, a cartridge is 55 watts. So a particular server, Moonshot server, fully loaded, is about 600 to 800 watts, which is much better than 2,000 or 3,000 watts a server that we normally typically run in a rack. Plus, we're getting the huge benefit of extreme performance. All right. Now, we know there's GPUs, we know there's FPGAs, but for us at the moment, at the time, we really like the fact that we're taking the existing technology, DSPs, and actually leveraging them in a completely different manner. All right. So what did we do about this? Well, all the different events that I showed you, the social media events, the metrics from the data center, the logging, we stream those at different intervals. And we can actually start correlating events from signals. And so that we had to build a new ontology, event ontology to actually do that. It was a bit of work, but we were able to do it. And what resulted out of this was a nice marketing campaign from HP. But we take chaos and make it nice, beautiful music. But here's the first use case that we did the work with. This is a subgraph. I mean, the graph is huge. This is just a subgraph of dependency between applications. All right, and so we started modeling what we're able to do now is understand how many through the DSP, how many of these different calls get made constantly, whereas we couldn't do that before. So, for instance, we can now measure how many times a call gets made a second to this particular database, for instance, or start counting how many connections happen between these two nodes. And this is part of our systems intelligence project to actually add low-energy processors to larger machines. And we call it atoms to galaxies because we have small machines here and large machines here. Yes, the UV2000 here and the ARM core here. So we're sort of looking at a heterogeneous multiprocessor cluster. And of course, because it's so colorful, everybody was excited about it. But this is just a start. We're going to be able to detect patterns in a rapid pace because we can basically parallel this thing. So those 3 million events a second can be parallelized across large numbers of nodes and then messaged back out to understand what's really happening. So we've had some challenges along the way. It hasn't been an easy road for us. There's only 2 persons on the team. They've allowed us a little bit of leeway because they know we're working on some really interesting things that we can bring back to the mothership. They give us a budget to work with. But we have had a few challenges. And one of the main challenges that we've had as an enterprise industry company is most people don't know what HPC is. So we are obviously want to teach people what HPC is all about. We want to be at conferences and talk about what we're doing. Industry wants to follow what other Valley companies are doing, right? Hadoop is a big one. Everybody wants to do Hadoop. Well, great. But you have to look at the problem slightly different or look at it the way the HPC community has been doing it. People are very comfortable with what they know. They don't want to step outside the bounds of what they know. That's just human nature. If you step outside the bounds, you're looked upon as a little strange, but the only way to innovate is you step outside the bounds. Otherwise, nothing happens. We also had to apply e-commerce availability to the HPC model. So because we are available 24/7 by 365, we had to bring our knowledge about scaling and our knowledge about availability to our HPC clusters. That's something that most of you don't have to worry about, but it's something that us as a PayPal or as an industry has to worry about. We don't think there's a box. Most people think there's a box. We don't even know a box exists. That's why we come up with these crazy ideas, and we potentially, hopefully, are very innovative about them. A lot of people don't have the ability to apply new technology. They're either scared of it, or they don't understand it, or they don't want to learn it. It's a very big problem. And that's why it's great to have younger folks, younger students pick up the new technology and move with it. But for existing companies, it's very hard to change the mindset of people who've been there for a long time to change their mindset about how things should work. Another thing is a lot of people can't take a vision and make it all the way to the end into production. You need to drive that all the way to the end. If you have a vision, you got to drive it to the end. And in terms of analytics, like Addison said yesterday, there's a shortage of data scientists, right? I think the shortage of data scientists is 230,000 for the next year or something ridiculously crazy. So if you want to change your name or your job to data scientist, you'll probably get a 50% increase in pay right away. All right, so how are we going to address these issues? Well, we're going to educate our peers. We're going to do brown bag lunches. We're going to do talks like this. We're evangelizing and socializing our ideas around HPC. We keep presenting HPC, the PayPal HPC technology to the world. We're formalizing a roadshow. PayPal is comprised of 12,000 people. We're formalizing a roadshow to actually showcase some of this work that we've been doing, because not everybody knows what we've been doing. We are hosting some birds of feathers. We did a couple at supercomputing the last few years, which were quite successful. And we're doing continual collaborations with people who are interested in talking to us about some of the problems we have or some of the problems they have that we might be able to help with. And so what are we looking at in the future? Well, in a post-split world away from eBay, we are going to be looking at high-performance data analytics, a new term that's been sort of bandied around in the last year. And in our atoms to galaxies architecture, again, atoms really small computers, galaxies being really large computers. We're focusing more and more on bringing the different aspects of computing into the toolbox and putting those technologies to use where they make sense. And we're going to be socially responsible and keep decreasing our power costs and our power consumption, because that's fitting for both our business needs as well as the world at large. So thank you very much for listening to our story, and I hope you glean something out of it, so the next time you make a payment through PayPal, you'll feel very comfortable that you're running it on HPC. Thank you. Yes? It's not particularly in my loop, but I think what will happen eventually, maybe not this year, but as part of the modeling that we're doing on the system, we're going to take this architecture and start moving it into different areas of the application stack. So for instance, the DSP work we're doing, we had a meeting with our senior developers just a couple of weeks ago. We're moving some of the DSP streaming analytics processing into various parts of the application where they make sense, only because when we can do a pattern detection in like 2 milliseconds, for instance, where it traditionally took 50 milliseconds, that saves us 48 milliseconds to do more stuff like what you're asking for, more models and more risk. Good.
So one of the things you said, I think, was that we're not at something that,
yeah.
that we can set up to actually say what
the shared memory. The traditional Hadoop model that they use is 5,000 nodes of Hadoop commodity hardware. Not every job needs 5,000 nodes, right? So you have to look at the workload and the job in particular and say, okay, this job doesn't need 5,000 nodes. It could probably run on 48 nodes. If you have a large shared memory where you can actually store the data worked on, it only made sense. Now, I'm not saying every job is going to run in 2 hours, but that particular job increased it. And they're so happy with that there's potential for more UV.